On July 21st, 2024, a robot the size of a small car stopped rolling across the floor of an ancient Martian lake, lowered a drill into a slab of pale mudstone rock, pulled out a sample that would ignite one of the most careful, most cautious, most electrifying announcements in the history of Planetary to Los Angeles. A group of scientists stared at images beamed back across nearly 200 million kilometers of empty space, and for a moment, nobody said anything at all. What they were looking at didn't look like geology. It looked like biology. And they knew immediately that they had to be wrong before they could dare to be right. This is the story of that rock. But it is also the story of a question humanity has been asking since the first person looked up at that reddish point of light in the night sky and wondered if anyone else was looking back. It sounds like a simple question. It is not. It may be the hardest question we have ever tried to answer, because unlike almost everything else in science, we cannot run the experiment twice. We have exactly one confirmed example of life in the entire universe, and it is us. Every theory, every equation, every mission, every billion-dollar spacecraft we have ever launched toward another world has, in some way, been built around the hope of finding a second example. Just one. Just enough to know that the universe did it more than once. For most of human history, the search for that second example was pure imagination. Ancient civilizations looked at Mars and saw a wandering red star, a herald of war, a god who bled light into the desert sky. The Babylonians tracked its movements across the heavens and recorded them on clay tablets. The Egyptians called it the Red One and gave it its own place among their pantheon. For thousands of years, Mars was not a planet to be explored. It was a symbol to be feared. Then, in the late 19th century, an Italian astronomer named Giovanni Schiaparelli pointed a telescope at Mars and described what he thought were long, straight lines crossing its surface. He called them canali, Italian for channels. But when the word reached English-speaking astronomers, it was mistranslated as canals, implying something built, something engineered, something intelligent. An American astronomer named Percival Lowell ran with the idea, building an entire observatory in Arizona dedicated to studying what he believed was a dying Martian civilization desperately building canals to funnel water from the polar ice caps to their parched cities. It was captivating. It was romantic. It was almost entirely wrong. But it planted something in the human imagination that never fully left. By the time actual spacecraft reached Mars in the 1960s and 70s, the fantasy of canal-building Martians was long dead, replaced by a colder, more sobering reality. The Mariner probes revealed a cratered, apparently lifeless world. And then in 1976, NASA's twin Viking landers touched down on the Martian surface and performed something remarkable. They scooped up soil and ran biological experiments, literally testing the red dirt of another planet for signs of metabolism. One of those experiments produced a result that, for a brief moment, looked like it might indicate life. The scientific community argued about it for years. Ultimately, the consensus settled on a different explanation. Unusual soil chemistry, not biology. The debate over what Viking actually found has never fully gone away, and some scientists still argue today that we may have detected life in 1976 and simply misunderstood the data. It remains one of the great unresolved footnotes in the search for life beyond Earth. For the following 2 decades, Mars exploration went quiet. Then, in 1996, a meteorite that had been sitting in Antarctic ice for thousands of years, a rock blasted off the Martian surface millions of years ago by an ancient impact and eventually captured by Earth's gravity, made headlines around the world, designated ALH 84001. The meteorite contained microscopic structures that some scientists argued resembled fossilized Martian bacteria. President Bill Clinton addressed the nation about it. For a moment, it felt as though the question of life beyond Earth had been answered. But as with Viking, the excitement cooled as competing explanations emerged. The structures could be explained by non-biological mineral processes. The debate was never fully settled, but the scientific consensus shifted away from the biological explanation. Once again, Mars had teased humanity with the possibility of life, and once again, it had refused to give a clear answer. This pattern, tantalizing evidence followed by careful, now often disappointing scientific scrutiny, has defined the search for Martian life for half a century. And it is precisely why what happened in 2024 mattered so much, and why the scientists involved were so deliberately almost painfully cautious about what they were willing to say. To understand why, you have to understand where Perseverance was standing when it made its discovery. The rover had spent years exploring Jezero Crater, a 30-mile-wide basin that satellite imagery revealed decades earlier to have once held a lake, not a puddle, not a seasonal trickle. A genuine long-lived body of liquid water, fed by a river that built a fan-shaped delta of sediment as it emptied into the crater, the same way rivers build deltas here on Earth. NASA chose Jezero specifically because ancient river deltas on Earth are extraordinary places to search for preserved signs of ancient life, since flowing water carries organic material and buries it in fine-grained sediment where it can be protected for billions of years. If life ever existed on Mars, scientists reasoned, a place like this was one of the best possible places to look for its fingerprints. In the summer of 2024, Perseverance left the delta and moved into a nearby region called the Neretva Vallis, an ancient river channel. There, it encountered a pale, layered rock, roughly the size of a doormat. Mission scientists gave it the nickname Sheyava Falls, after a waterfall in the Grand Canyon. And when the rover's cameras got close enough to examine its surface in detail, they revealed something that made the entire science team lean in. Scattered across the rock's surface were dozens of small, irregular, ring-shaped spots, pale rims around dark centers, that scientists began informally calling leopard spots. Because of their resemblance to the markings on a leopard's coat, running through the rock in branching, vein-like patterns were streaks of white material, later identified as calcium sulfate, evidence that water had once flowed directly through cracks in the stone. Nearby, the rock's chemistry revealed something else: organic carbon, a kind of carbon-based molecules that serve as the building blocks of life as we know it, embedded directly within the rock itself. None of these things alone was proof of anything. Organic molecules can form through purely chemical processes with no biology involved whatsoever. They've been found on comets, in meteorites, in the atmospheres of gas giants, in places no one seriously believes ever hosted life. But it was the specific combination and specific chemistry, what the leopard spots contained, that elevated this rock beyond anything Perseverance had found before. Using the rover's onboard instruments, scientists detected that the dark centers of those leopard spot rings contained two particular minerals: vivianite, an iron phosphate mineral, and greigite, an iron sulfide mineral. On Earth, these specific minerals can form through reactions that involve microorganisms. Certain bacteria are capable of using iron and sulfur compounds as part of their metabolism, essentially breathing through chemical reactions the way we breathe through oxygen, and in doing so, they can leave behind vivianite and greigite as byproducts. Finding this precise mineral pairing embedded in organic-rich rock, sitting inside a rock formed by water that once flowed through an ancient river system, was the closest thing NASA had encountered in the mission's history to what scientists call a potential biosignature, chemical pattern that life could produce, sitting exactly where ancient microbial life could plausibly have existed billions of years ago. This is the moment the mission's scientists, including the deputy project scientist at NASA's Jet Propulsion Laboratory, chose their words with extraordinary precision. They called Sheyava Falls the strongest potential biosignature ever detected on Mars. Not proof, not confirmation, not evidence of life. Potential biosignature, a pattern consistent with what biology might have left behind, but not something that rules out non-biological explanations. And that caveat is not scientific timidity. It is scientific integrity. And it exists for a very specific reason. The exact same mineral reactions that microbes can produce can also occur through purely chemical processes that involve no life whatsoever, particularly when rocks are exposed to certain temperatures and chemical environments over long spans of geological time. On Earth, geologists can usually tell the difference between a biological leopard spot and an abiotic one by examining it under laboratory conditions with equipment far more sensitive than anything that can be flown. To Mars and packed into a rover the size of a car, Perseverance is an extraordinary machine, but it is also, by necessity, a limited one. It can detect chemical signatures. It cannot, on its own, definitively distinguish biology from geology across 200 million kilometers of vacuum, which means the only way to know for certain what created those leopard spots is to bring the rock home. This is where the story of Sheyava Falls collides with one of the most ambitious and most troubled endeavors in the history of space exploration: Mars sample return. For years, NASA and the European Space Agency have been developing a plan to retrieve the sample tubes Perseverance has been carefully drilling, sealing, and catching across Jezero Crater. Launch them off the Martian surface using a small rocket, rendezvous with a spacecraft in Mars orbit, carry them back across the solar system to laboratories on Earth. It would mark the first time in history that material deliberately collected from another planet's surface was physically brought home for analysis. It would also be staggeringly expensive and staggeringly difficult. Independent reviews in recent years estimated the mission could cost upward of several $billion and might not deliver samples to Earth until the mid-2030s at the earliest. Timelines and budgets that triggered serious internal debate within NASA about whether the original architecture was sustainable. The agency has since been exploring simplified, less expensive alternatives, some involving newer commercial rocket technology, in hopes of getting the samples home sooner and for less. As of now, the exact path, timeline, and price tag of Mars sample return remains one of the most consequential open questions in American space policy, a question made dramatically more urgent by what sits inside tube number 29, sealed inside Perseverance's belly, containing a piece of the very rock that started all of this. Consider the strange, almost unbearable irony of that. Somewhere on the surface of Mars right now, there may be physical evidence, sealed in a titanium tube, that could answer one of the oldest questions in human history. And it is sitting there, waiting, because the rocket, the spacecraft, the multi-billion-dollar orchestration required to bring it home does not yet exist. Humanity may have already found the proof, simply haven't built the ship to go get it. To understand why scientists believe finding this proof matters so profoundly, it helps to widen the lens beyond Mars entirely, out to the broader scientific effort to understand how common, or how rare, life might be across the universe. In 1961, astronomer Frank Drake proposed an equation, now famously known as the Drake equation, that attempted to estimate the number of technologically communicating civilizations that might exist in our galaxy. The equation multiplies together a chain of probabilities: the rate of star formation, the fraction of stars with planets, the fraction of those planets that could support life, the fraction where life actually emerges, the fraction where that life becomes intelligent, the fraction that develops detectable technology, and the length of time such a civilization survives long enough to be noticed. Every single term in that equation, except the first, remains deeply uncertain. Depending on which numbers scientists plug in, the equation can suggest the galaxy is teeming with intelligent life, or that we are catastrophically, perhaps entirely alone. The equation was never meant to produce a definitive answer. It was meant to organize the questions. And for over 60 years, that's exactly what it has done, forcing scientists to confront just how little we actually know. That uncertainty leads directly into one of the most haunting ideas in all of science: the Fermi paradox. Named after physicist Enrico Fermi, who is said to have posed the question over lunch with colleagues in 1950, the paradox asks a deceptively simple thing, and contains hundreds of billions of galaxies, each containing hundreds of billions of stars. Then statistically, intelligent life should have arisen many times over, and at least some of those civilizations should be advanced enough and old enough to have spread across the galaxy by now. So where is everybody? Why has the sky remained silent? Why, in all our decades of listening with radio telescopes, scanning the heavens for signals, have we heard nothing at all? There are dozens of proposed answers to the Fermi paradox, and none have been confirmed. Perhaps intelligent life is extraordinarily rare, a cosmic fluke that happened only once here on this one blue planet circling an unremarkable yellow star. Perhaps civilizations tend to destroy themselves before they can reach the stars. Through war, through climate collapse, through technologies they create but cannot control. Perhaps advanced civilizations exist, but have no interest in communicating with a species as young and as primitive as ours. Or perhaps, and this is the possibility that Mars quietly, patiently refuses to rule out, life itself is common but complex, intelligent, technological life is the rare part. Perhaps simple life, microbial life, the kind that might have left leopard spots in an ancient Martian riverbed emerges relatively easily wherever conditions allow. Perhaps the leap from simple life to complex life, the leap that took Earth nearly 4 billion years to make, is the true bottleneck of the universe. If that is true, then finding confirmed evidence of even simple, ancient microbial life on Mars would not just answer the question of whether we are alone. It would fundamentally reshape our estimate of how common life is across the cosmos, because it would prove that life can arise independently, at least twice, in a single solar system, on two entirely different worlds, under two entirely different sets of conditions. And if life could start twice here, in our own cosmic backyard, then the odds that it has started elsewhere on the thousands of exoplanet scientists have already discovered orbiting other stars would shift dramatically in favor of a universe far more alive than we ever dared to assume. This is why Mars has never really stopped mattering. Even through the decades when its surface looked cold, dry, and utterly dead. Because roughly 3.5 to 4 billion years ago, the evidence increasingly suggests that Mars was not the desolate world we see today. It had a thicker atmosphere, shielding its surface from the worst of the sun's radiation. It had rivers, lakes, and quite possibly, according to some orbital surveys, entire oceans covering parts of its northern hemisphere. For a window of time that may have lasted hundreds of millions of years, ancient Mars looked, in some fundamental ways, disturbingly like ancient Earth, and ancient Earth, during that very same window of time, was busy inventing life. Something happened to Mars that never happened to us. Its core cooled, its magnetic field faded. Without that magnetic shield, the solar wind, the relentless stream of charged particles pouring off the sun, began stripping away the Martian atmosphere. Molecule by molecule, over millions upon millions of years, until the thick blanket of air that once could have supported liquid water thinned into the frozen, nearly airless world we see today. Mars didn't just lose its water. Conditions that made complex chemistry and possibly biology sustainable. It is, in a very real sense, a preview of what could eventually happen to any world, including our own. If the deep planetary processes that protect a habitable surface ever fail, that transformation is precisely why Jezero Crater is so scientifically precious. Its ancient lakebed and delta sediments were laid down during exactly the era when Mars still had the ingredients for life. And then, crucially, that sediment was buried, protected, essentially entombed, before the worst of the planets. Radiation exposure could destroy any organic material trapped inside. Shavah Falls sat in that entombed layer for potentially billions of years, undisturbed. Until a robot from another planet drilled into it in the summer of 2024. It is worth pausing here to consider the sheer audacity of that sentence. A machine engineered by human beings, launched from Cape Canaveral, guided across 200 million kilometers of interplanetary space, landed with pinpoint precision inside a crater using a never-before-attempted sky crane maneuver that lowered the rover on cables like a spider descending on silk, has spent years autonomously navigating an alien landscape, selecting which rocks to examine, drilling into their surfaces, transmitting the chemical fingerprints of an ancient world back to laboratories on Earth. Perseverance is not simply a scientific instrument. It's in skepticism that has killed countless ambitious space missions before they ever reached the launch pad. Its predecessor, Curiosity, faced its own near-disastrous entry, descent, and landing sequence in 2012, maneuver so complex that mission engineers nicknamed it the 7 Minutes of Terror. Caused the radio signal delay between Mars and Earth, meant that by the time controllers on the ground received confirmation that the spacecraft had entered the Martian atmosphere, the rover had already either landed safely or been destroyed. There was no way to intervene. Humanity's multi-billion-dollar machine was entirely on its own, hurtling toward the surface of another planet at 8 times the speed of a rifle bullet. It was nothing anyone back on Earth could do but wait. Perseverance inherited that same terrifying landing sequence, refined and improved, and added something new. A helicopter, 4-pound solar-powered rotorcraft named Ingenuity. Tucked beneath the rover's belly, designed as a technology demonstration that few expected to succeed, since no one had. ever flown a powered aircraft in an atmosphere as thin as Mars's, a mere 1% the density of Earth's, engineers gave Ingenuity 5 test flights and modest expectations. It flew for the first time in April 2021, and by the time its mission finally ended in January 2024, after its rotor blades were damaged in a hard landing, it had completed 72 flights, an achievement almost nobody had dared to predict, and one that fundamentally proved that powered flight, not just wheeled exploration, was possible on another world. It was, in its own quiet way, the Wright brothers' moment for an entire planet. All of this, the perilous landing, the helicopter, the years of patient roving, the careful selection of Jezero Crater, based on satellite evidence of an ancient lake, was building toward a single moment, encountering a rock that might carry, sealed inside its ancient mineral structure, the fingerprint of a Martian ecosystem that lived and died before complex life had even emerged on Earth. But Jezero Falls is not the only frontier in the search for life beyond our own planet. And to understand why NASA's Martian discovery landed with such force in 2024, you have to understand what else was happening in the broader search for life across the universe at the exact same time. Roughly 240 light-years from Earth, orbiting a small, cool star, sits an exoplanet called K218b, a world roughly 8.5 times the mass of Earth. Orbiting within its star's habitable zone, the region where conditions could theoretically allow liquid water to exist, using the James Webb Space Telescope, the most powerful space observatory ever constructed, astronomers have detected chemical signatures in K218b's atmosphere, including in preliminary and still debated observations, a molecule called dimethyl sulfide, compound that on Earth is produced almost exclusively by living organisms, primarily marine phytoplankton. The detection remains contested within the scientific community, with some researchers questioning the statistical confidence of the signal and others proposing non-biological explanations, and further observations will be required before any firm conclusions can be drawn. But it represents something extraordinary in its own right, for the first time in human history. Our instruments are sensitive enough to search for the chemical breath of life on a planet orbiting a completely different star. Consider what it means that humanity is simultaneously drilling into ancient riverbeds on Mars and analyzing the atmospheric chemistry of planets, trillions of miles away, using instruments so precise they can detect a handful of specific molecules mixed into an atmosphere we cannot even see directly, only infer from the way starlight filters through it during a transit. We are searching for life at every scale accessible to us in our own solar system and far beyond it, using tools that would have seemed like pure fantasy to the astronomers who once mistook Martian canals for alien engineering. And this search is accelerating. Yes. NASA and its partners are already developing the next generation of missions built specifically around this question. The European Space Agency's Rosalind Franklin rover, delayed by the war in Ukraine after its planned Russian launch partnership collapsed, is being rebuilt to launch toward Mars with a drill capable of reaching 2 meters beneath the surface, far deeper than Perseverance can go, deep enough to potentially reach organic material that has never been exposed to surface radiation at all. Engineers are studying nuclear thermal and nuclear electric propulsion systems that could cut travel times to Mars dramatically, reducing the radiation exposure and psychological toll on future human crews. Commercial companies are racing to develop the heavy-lift rockets, reusable spacecraft, and orbital infrastructure that could eventually make crewed Mars missions a realistic possibility within the coming decades, missions that could, for the first time, put human geologists, not robotic proxies, directly at sites like Jezero Crater, with the ability to make judgment calls no algorithm could replicate. Because that is, ultimately, the deepest and most humbling lesson embedded inside the story of Jezero Falls. A robot found something extraordinary. But a robot cannot fully resolve the mystery it found. It can gather the clues, cannot on its own deliver the verdict. Requires human hands, human laboratories, and quite possibly someday human beings kneeling directly in the Martian dust, examining with their own eyes the layered stone that may hold the oldest secret in the solar system. So where does that leave us, standing here in 2026? Looking back at a discovery announced 2 summers ago, a sample sealed in a titanium tube, sitting in the dust of an alien crater, waiting for a mission that does not yet exist to carry it home. It leaves us in the position humanity has occupied again and again throughout the history of this search. Not with an answer, with a threshold. Viking gave us a threshold in 1976, and time moved past it without resolution. The Mars meteorite gave us a threshold in 1996, and the debate faded without consensus. And now, Sheava Falls, sealed and waiting somewhere in Jezero Crater's fine red dust, gives us another. Perhaps this time, the story ends differently. Perhaps this is the sample that finally crosses from potential biosignature to confirmed evidence. The discovery that future generations will point to as the moment everything changed. Or perhaps it won't. Perhaps like a LH84001. Further analysis will reveal a purely chemical explanation. And the leopard spots of Sheava Falls will join the long list of tantalizing near misses in humanity's search for a second Genesis. Science does not owe us the answer we want. It only owes us the truth, whatever that truth turns out to be. Disappointment is exactly what makes this moment in history so electric. We do not yet know how this story ends. Nobody does. Not the scientists at JPL, not the engineers designing the sample return architecture, not anyone alive today. What we do know is this. Somewhere on the dusty floor of an ancient Martian lake, there is a rock with leopard spots pressed into its surface. Formed at the exact moment in the planet's history, when it still had the conditions to nurture something alive. That rock has been waiting there for roughly 3.5 billion years. Since before complex life crawled out of Earth's oceans. Since before dinosaurs. Since before the continents on our own planet had finished arranging themselves into the shapes we would recognize today, it waited through the death of the Martian atmosphere. Through billions of years of solar radiation scouring the surface above it, through the entire span of human civilization, from the first campfire, to the first telescope, to the first rocket that ever left Earth's gravity. It waited silently until a machine built by curious primates on a neighboring world finally reached down, drilled into the stone, and asked it the oldest question there is. And now, that question sits between us and the stars. Patient, sealed, and waiting for humanity to finish building the bridge that will finally bring the answer home. When that bridge is complete, whenever it finally is, we will know, one way or another, whether the universe made life only once, in this one fragile, blue corner of the cosmos, or whether it made life at least twice, right next door, on a cold red world we have been watching, wondering about, and